Hello, I'm Noah Holkabor. I'll be going into my junior year at Grand Valley State University, and today I want to walk you through some of the strengths and limitations of using photographs to study tree architecture, specifically focusing in on a destructive conformation and a pilot study involving 4 species. First, a little bit of background. So the woody part of any tree has 2 main tasks it's got to accomplish. It's got to transport water and it's got to provide structural support. And because trees are constrained by various biomechanical and physical factors, how they do these tasks can be studied using various mathematical models. We use Murray's Law, which predicts area preservation at a branching point and is an estimate of hydraulic efficiency. We use West-Brown-Inquist model, which is about mass allocation throughout the tree architecture. And we use the uniform stress model, which is about the support of the limbs, and it takes the angle of branching into account. So why a non-destructive method? Well, all previously published research has taken their measurements destructively, which has its benefits in that it offers accurate and precise data, but it limits the potential avenues of inquiry. A non-destructive methodology would allow for longitudinal studies, it would allow for large-scale studies, and it would potentially make the field more accessible and cost-effective in general. So to assess this, our destructive conformation, simply our goal was to determine if measurements taken from photos could even offer a valid alternative to destructive measurements. So we took an Acer rubrum, which you can see kind of in the middle of that photo there, which was 33.5 centimeters in DBH and 23.4 meters tall, and we cut it down, and each of its branching points, what we call nodes, along a leading path, were photographed. And then we compared measurements that were taken directly, physically from the nodes, and that we took from the photographs using ImageJ. Now the photographs that we used, they were taken in the lab from cut node sections, and there's an example photo there on the right. And this was due to a miscommunication. The original plan was to have those photos taken before the tree was cut down. And it's a bummer that didn't happen. However, these results still hold promise in that they show ideal conditions where photo resolution, lighting, perspective distortion, those things are controlled for. So there's still a valid methodology here. And to jump right into our results, we found a significant correlation between the direct and photo measurements, which is, I suppose, to be expected because we're measuring the same thing, same point on a tree. If you look at this figure here, we have the direct mother on the x-axis and the photo mother on the y. And we had an r-squared of 0.988 with a p-value of less than 0.001, so there's clearly a strong correlation there. But when we look over on the right, we can see that in those larger nodes especially, the triangles here being the photos and the circles being the direct, when we see the mother radius compared versus the nodes, there's this consistent over-optimization in the larger, earlier nodes that diminishes as they get smaller. And though we're still trying to figure that out, we are still confident that photos can offer valuable data, especially because it's so close and because our models, they use relative measurements of the daughters and mothers, not so even an error in the gross measurements. If the relative stuff is still correct, the model is still working just fine. But to hop into our pilot study, the goal here was just to assess if photos could generate sufficiently accurate data to distinguish between species for various tasks, or within a single species for in between the tasks and models for that species. Those are just some example photos of ginkgo there on the right from the study. But our methods, we took scaled photos of the first branching point, the first node for 4 species, and there's some example photos there on the right. We used Fagus grandifolia, Quercus rubra, Acer sacrum, and Ginkgo biloba. And for each species, about 30 trees, we measured their DBH and took photographs of them. And all of these trees in our study, they were located in West Michigan parks, forests, or in the case of Ginkgo biloba, in the city streets of Grand Rapids. So in ImageJ, we then measured the characteristics of node 1. You can see that the mother is there before the branching point, then you have the 2 daughters after the branching point, and of course that node angle. Then we took those mother-daughter ratios and the branch angle in the case of the USM, and used them to quantify branch geometry according to the various models. So jump into our results. First thing I wanted to direct your attention to this chart here on the left. You can see on the x-axis we have the log Murray mothers, and on the y-axis we have the log Murray daughters. All the charts are going to kind of be set up that way, and that means that the smaller nodes are going to be to the bottom left, and the larger nodes are going to be to the top right. And you can see that we have the blue line and the blue circles there, which are our observed, and the red line and the red triangles, which are our predicted. Now, those predicted values, they were actually calculated using the residuals from the observed regression and then applying them to the predicted, which is just isometry. And that's to kind of make a more fair comparison because it'd be too easy to find significance comparing the observed to just perfect isometry. And I also want to quick point out that in this table here is the predicted regression information, and that's omitted from the future tables, and that's just because it's always going to be the same. The y-intercept is always going to be 0 or practically 0, and the slope is always going to be 1. But jumping into the actual results for Fagus grandifolia, we see that all three models show a negative allometry with an increasing safety margin associated with increasing node size. And this is while all of them have an R-squared of over 0.95, which is a pretty good indicator that there's something being offered by these photos. And interpreting that for each model, looking here at the left again at Murray's law, we can see that as the nodes get bigger, the deviation from the predicted also gets larger. And that means that for Murray's, that those larger nodes are going to be less hydraulically efficient. They're less optimized for hydraulic efficiency, but they're also going to be less likely to experience an embolism. That's why it's called a safety margin. And so as the nodes get larger, they get less hydraulically efficient and also less likely to experience an embolism. In the middle, for the West-Brown-Inquist model, that is talking about total mass. So that means that as the nodes get larger, they're going to be supporting less mass than they theoretically could. And for the USM, talking about the support of branches, that means that as those nodes get larger, they are going to be supporting branches that are maybe less massive or at a less risky angle, which will mean some sacrifice for the tree in terms of like the size of their branches, but those branches will also be less likely to break off or buckle due to their own weight or due to the stress imposed by wind or snow or things like that. Moving over to Quercus rubra, here again, we also have R-squareds all over 0.95. And I want to talk about it briefly because, again, all three models show negative allometry with increasing safety, with an increasing safety margin associated with increasing node size. It's the exact same story of Acer sacrum, which I just talked about. Murray's law, as the nodes get larger, they are less hydraulically efficient, less likely to experience embolism. West-Brown-Inquist, as the nodes get larger, they're supporting less mass than they theoretically could. USM, as the nodes get larger, the branches are less likely to break off. And why this is important to our study is because Quercus rubra and Fagus grandifolia are relatively closely related species, and here they are behaving similarly, which I think is exactly what we'd biologically expect. We would expect related species to have similar branch architecture, and here that's happening. And I think that lends some credibility to photographic methods and just to this kind of type of study in general. But moving on to Acer sacrum, again for the nodes 1 for about 30 trees. In this case, all models show isometry for Acer sacrum, and this indicates optimization and that there's no detectable safety margin. That means that for Murray's law, as you can see, it's generally pretty close to the predicted as it goes, and there's no detectable difference from Mariankova. And all of our R-squareds all of our adjusted R-squareds, all of these have been adjusted R-squareds, I should say, was above 0.95. But in this case, that means that as throughout the node sizes, they're going to be optimized for hydraulic efficiency, but Acer sacrum might be more susceptible to embolism. For the West-Brown-Inquist, that means that throughout the node sizes, they're going to be supporting about as much mass as they theoretically could. And for the USM, that means that those branches for Acer sacrum are probably going to be larger, maybe at more risky angles, and that will offer some benefits for the tree, but it'll also mean that those branches might be more likely to break off under stress. And what I really want to hammer home here is that this demonstrates that the data derived from photos can distinguish between species. It's not just telling the same story all the time, because these Acer sacrum results are distinct from the previous two, which really lends some credibility to the photographic method and shows that it has an ability to distinguish between species and kind of give useful, interesting results. And before I move on to ginkgo biloba, I want to have a quick aside and just bring up that the optimization for node 1 of Acer sacrum, what I just talked about, is really similar to nodes 1 through 30 of the destructive Acer rubrum, and this is kind of a comparison of opportunity. We didn't expect it to make this comparison, but if you look here at this table on the right, Acer rubrum and Acer sacrum, they are optimizing very similarly. Generally, their models are showing isometry. And we see this deviation for the West-Brown-Inquist for Acer rubrum, and there's the figure for that on the left. And even though our ANCOVA picked up a difference, we want to interpret this cautiously because, as we can see, the deviation from isometry is actually very slight, and so that might not be an actual deviation from isometry. But what's really important here for our study is that these similarities suggest that perhaps, at least for Acer, node 1 might not just be a good indicator of what's happening at node 1, but it might be a good gauge of what's happening in the overall functional architecture of a tree, because here we have node 1s of Acer behaving similarly to nodes 1 through 30 for another individual Acer. And then here's just the data for all of that if you're particularly interested. But I want to get us back on track and move on to ginkgo biloba because it's really interesting. For ginkgo biloba, we had a mix of results and this indicates that photos aren't just distinguishing between species, but even inside of a single species, it could distinguish in between the models. And I do want to just note again that here all our adjusted R-squared values are above 0.95, which has been a pretty kind of consistent trend and really bolsters my confidence in this photographic method. But kind of interpreting the models for Murray's law on the left, we found a deviation from isometry. So that means that as the nodes get larger, they're going to be less hydraulically efficient and less likely to experience embolism. For the West-Brown-Inquist, again, deviation from isometry. That means that as the nodes get larger, they're going to be supporting less mass than they theoretically could. And with the USM, in this case, we found isometry. And that means that those throughout the various node sizes for ginkgo, those branches are going to be potentially at more risk of breaking off. But I want to have a couple notes in that the Murray and West-Brown-Inquist, those were marginally significant, which we're defining as a p-value between 0.1 and 0.05. However, we think that is still compelling as the use of photos is going to increase the risk of type 2 error, especially at those larger nodes. And it also should be noted that it's possible that a negative allometry might exist for the USM at larger nodes, but that our methods, our sample size, and the fact that we didn't get a whole lot of large ginkgo in our sample couldn't capture it. But that said, I do think that this still does indicate, at least at face value, that the photographic method is able to not just distinguish between species, but even inside one species, distinguish between the models. And just to kind of wrap some things up in a summary, I want to bring us back to the destructive conformation and just pull back up the fact that it seems that photos certainly can approximate direct measurements, apparently especially at smaller node sizes. And even though we see this overestimation occur, I think that there's still validity here, both because the measurements were still pretty close, especially looking at the smaller nodes, and because our models rely on a relative relationship between the mothers and daughters. And so a deviation in the gross measurements, like the centimeters, if it's consistent, wouldn't actually interfere with the models if the ratio is correct. Now, to bring it back to what I was just discussing, the fact that data from photos can show species-specific trends that logically fit what we biologically expect. Looking at this table here that compares all 4 species, we can see that Fagus grandifolia, Quercus rubra, optimizing similarly, and they're closely related. But that's compared to Acer sacrum, which is the complete opposite, indicating that photos truly can tell differences between species. They're not just saying the same story over and over again. And then we have ginkgo biloba, which is showing us that even inside a single species, photographs have the power to distinguish between individual models. And so taking this as a whole, I think that it supports the conclusion that a photographic method could play a valuable role in future study. It's certainly not going to replace destructive measurements, and nor should it. They offer accurate and precise measurements that are valuable in some cases, but I think it could find its niche, especially in longitudinal studies, which would be impossible destructively, and when gathering large amounts of data that would just be very hard to do destructively. And so that's really what I've got on this topic. But before I completely wrap up, I want to just look forward a little bit and note that we're constantly improving our methods, whether that's getting scale bars up in trees close to nodes or messing with photo stuff or ImageJ stuff. In the center there, you can see a picture of a map of our plot study. I actually took measurements of over 150 individuals and took photos of them in a plot. And so we're hoping that will reveal some interesting effects on kind of maybe neighbor effects. And finally, microanatomy is something we're really interested in comparing to see if there is a relationship between the microanatomy of a species and its overall architecture. But this is the literature I cited earlier, and of course it's just a selection from what's out there. And finally, thanks. I want to thank Gary Greer for excellent mentorship over the years I've been working with him and all he's taught me. I want to thank Stephen Poloski for his work on the destructive conformation aspect of this, and Brendan May, Nicole Foy, and all the other students who have been involved in Gary's lab and this project over the past few years. I want to thank Grand Valley State University for the funding through the listed grants. And of course, I want to thank you for listening to this presentation. I really appreciate you taking the time to come see what I have to offer. But if you have any questions or suggestions for how I can improve, I would really love to hear them. I'm really looking for the insight of the scientific community on this one. And so you can use the Botany conference system, or if it's later or that's not working, feel free to reach out to me through email. My contact information is up there. But thank you very much. I hope that you have a lovely rest of your day and that you enjoy the conference.